Good morning, everyone. Thank you for tuning in for this presentation. My name is Rafael Rodriguez. I am a second-year graduate student in the Physical Metallurgy and Materials Design Lab at the Material Science Department in the University of Pittsburgh. The topic of this presentation, as you can read from the title, is microstructure characterization and post-heat treatment design for a high-strength low-alloy steel strengthened with Fe2Si-Ti precipitates. Before starting, I would like to acknowledge first my fellow co-workers on this study, mainly Xiong, Soumya Sridar, Zhangwei Wang, and my advisor and lab director, Dr. Xiong. Also, I would like to thank the Office of Naval Research for providing the funding to carry out this investigation. Let's get started. At the core of the motivation of the study is the high technical interest of high-strength low-alloy steels, or HSLA steels for short. HSLA steels like HSLA 80, HSLA 100, and HSLA 115 are proven to be outstanding candidates for the naval and automobile industry. This is mainly for three reasons. First, the low cost and high strength. Second, the excellent low temperature toughness. And third, their good weldability. The low carbon content of these steels provides them with good resistance to hydrogen-induced cracking. The dissolution of cementite during the heat treatment provides the necessary carbon content for the precipitation of M2C carbides, which then imparts excellent impact toughness results. Finally, the expected decrease on strength associated with the lesser amount of carbon is offset by the precipitation strengthening effect of copper. Perhaps the most remarkable characteristic of these steels is this last one. The combined strengthening effect of copper and M2C carbides in fairly low amounts, less than 3%. Now, in recent years, there has been an effort to explore precipitation hardening of steels with intermetallic phases. In particularly, the iron silicon titanium system has received attention since it has been shown that it can form a high volume fraction of intermetallic precipitates. It has been reported with the titanium and silicon are added to low carbon steels that metastable Fe2Si-Ti intermetallic phase can precipitate. Studies confirm that this is an L21 order phase able to precipitate in much higher volume fraction, even above 6%. This then leads to the possibility of having steels with low density elements that have suitable hardening behaviors, which then represents a unique advantage as it directly addresses the always challenging goal of designing materials with low weight and high strength. It is for these reasons then that the goal of this project was to design an HSLA steel with the L21 phase as its major strengthening precipitate, as well as its heat treatment. The methodology and the experimental plan that we carry out to achieve this goal is laid out here for you. By following the CALPHAD-approach and empirical models, we develop a high-throughput ICME framework that allows to explore these steel's multi-component system and screen compositions that would maximize the volume fraction of the desired L21 phase while minimizing the other detrimental phases common on the iron silicon titanium system, such as the Fe2Ti C14 LAF phase. Selecting a pair of the best composition candidates, we casted 20 grams ingots by via of arc melting. Based on the microstructure predictions obtained by CALPHAD and in-house developed models, we came out with both the homogenization and aging temperature as well as the aging times for the study to carry it out, to study the full picture of the aging evolution. Finally, using backscatter electron microscopy with energy dispersive X-ray spectroscopy, EDS, as well as atom probe tomography, we characterize the microstructure of the samples in their different heat-treated conditions. And lastly, we use Vecchis hardness testing to quantify the mechanical properties of the sample. Now, after screening thousands of compositions, here in the table you can see the best two candidates, and we are listing here for you the most relevant element composition of both samples. The design composition, as you can see in the first two rows, is the retrieved values from the ICME model, while the cast values on the last two rows, those are coming from the casted ingots, the EDS data from the casted ingots. Both samples you can see are very similar in their composition. For the majority of the elements, they are pretty much the same, even including for copper. You see there's only a small difference. But the main difference between the two samples, S1 and S2, is the titanium silicon ratio as well as the niobium content. The niobium in S1 is much higher than in S2. Now, going forward with the CALPHAD predictions, the equilibrium phase, CALPHAD allows to compute the equilibrium phase fraction and the non-equilibrium solidification behavior for our two samples. These allow us to get an insight when designing these materials to what type of phases and microstructure we want, so we can tune, for example, temperatures, homogenization and aging temperatures in order to get the goal of maximizing, in this case, L21 and minimizing the lab phase. In the top two images, to be specifically, we observe that we have the phase fraction of both samples versus temperature. And we see that for both samples, the amount of copper and MX phase is expected to be pretty much the same. MX in this system is going to refer to titanium carbides. Also, for both samples, we see that the L21 phase fraction is similar. If we, for example, take 500 degrees C, we see that for both samples, we have a prediction between 8 to 9% volume fraction of L21. The only difference between the two samples regarding L21 we see is just the temperature window upon which the L21 is expected to exist. In the case of S1, the temperature window is much smaller than in the case of S2, and that's due because of S2 has a higher content of titanium and silicon. Now, these titanium silicon difference plays a more drastic effect when it comes to see the effects in the lab phase. Clearly, we notice the drastic difference between S1 and S2, where S2 has a very narrow, condensed temperature window where the lab phase can exist, while in the case of S1, the lab phase can exist all the way up to, is predicted to exist all the way up to 1200 degrees C. If we now focus at the last two images, the non-equilibrium solidification behavior, we see that the outcome, the predicted outcome is the same for both samples. The ASCAS microstructure is expected to have the BCC ferrite accompanied with some amount of the MX, the FCCM, the titanium carbide phase, and the unavoidable lab phase is expected to be seen on the ASCAS microstructure. Here in this next slide, you can see backscatter images of the ASCAS microstructure of both samples S1 and S2 at 3 different magnifications. And we indeed see that the predictions, the CALPHAD prediction for the non-equilibrium solidification behavior are confirmed. EDS results not showing here, but confirm that the black discrete squiggly features that you can see are predominantly the Fe2Ti C14 lab phase, while the black squarish features correspond to the MX or the titanium carbide phase. These latter ones are hard to find because of the low volume fraction that they have, but they are easy to identify in the sense that those squarish morphology correspond to these titanium carbides. We see that now, strangely though, these are not the only features in the ASCAS microstructure. We can also point out here, as you can see on the top right corner, that these ASCAS samples shows a non-well homogenized microstructure, and this is exemplified by the fact that we found some copper spheres that were not fully dissolved into the matrix. In the case of S1, and we also saw some like patches, some aluminum cluster patches spread throughout the S2 as gas microstructure. But again, this is common of as gas microstructure. Now, then, in order to remove this segregation and have a more uniform microstructure, a homogenization heat treatment needs to be carried out. In order to select the homogenization temperature, we again rely on CALPHAD. Based on these phase fraction predictions and the limits of our lab furnace, we set the temperature for the homogenization to be 1200 degrees C. Based on these, we then expect that for S1, the homogenized microstructure should only consist on the BCC ferrite with a very minimum amount of lab with MX, and in the case of S2, the ferrite should only be accompanied by the MX. At this point, it's relevant to point out that when CALPHAD models, for example, the L21 phase, it does it as a line compound, like a line stoichiometric compound. This means that the L21 phase is assumed to have no solubility whatsoever of any element. And this is going to be important now, moving on to the experimental results. Here again, you have another set of backscatter SEM images of S1 and S2 at 3 different magnifications detailing the homogenized microstructure. We see that these images show a slight disagreement with the predictions that CALPHAD did. After 2 hours at 1200 degrees C, S1 does have a minimum amount of lavas and MX as predicted, but to our surprise, the grain boundaries are decorated with a white color L21 phase, something that CALPHAD didn't account for. S2, on the other hand, shows a cleaner and a more uniform microstructure, but still a minimum amount of as-cast retained lavas continues to show up. L21 in S1 is exclusively along the grain boundaries. Then if we compare the S1 and S2 images, it's clear that the L21 is refining the grains by hindering grain boundary motion, something that was not expected, but is interesting to see, since having phases that work both as a strengthening precipitate and a grain refiner is a huge advantage, because this can lead to improvement in mechanical properties. EDS results of the L21 microstructure told us that this phase has a finite amount of niobium solubility. Niobium in steels is well known to segregate to grain boundaries during heat treatment. This then allows to speculate that the diffused niobium to the grain boundaries might be acting as a heterogeneous nucleation site for the L21. And CALPHAD again, since assumes L21s to be as a line stoichiometric compound with no solubility, then won't be able to predict this type of behavior. Now, if we move forward to the aging predictions now, we again rely on CALPHAD phase fraction. In this regard, we want to select a temperature that yields a maximum of L21 while keeping a minimum amount of lavas. Therefore, based on this phase fraction, we decided to choose the temperature, the aging temperature of 500 degrees C to carry out the studies on aging, to study the aging kinetics of this system. Furthermore, in order to define the aging time to study, an aging model was developed. The main parameter for this model is the interfacial free energy. So using information from the aging behavior of L21 phase in the iron titanium silicon system, our model was calibrated, and the best fit for the interfacial free energy was set to be the constant value of 145 millijoules per meter squared. This best fit is shown in the left figure here. This figure shows the overlapping of the L21 aging behavior reported in literature in the context of the iron titanium silicon system, and the corresponding simulation predictions of our model. The figure on the right corresponds to our aging model applied to our S1 and S2 HSLA compositions at 500 degrees C. These predictions allow us to evaluate the volume fraction of L21 at multiple aging times. It is worth notice, though, that in both samples, already like on the onset of 2 hours of aging, the expected volume fraction of L21 is above 8%. This corresponds to the previously mentioned advantage of this type of intermetallic phase that has this unique characteristic of being able to abundantly precipitate, something that is not as common for another type of precipitate as copper and M2C carbides on previous HSLAs. Now, here you have a third set of backscatter SEM images. These are corresponding to the microstructure of S1 and S2 age at 500 degrees C at multiple aging times. We clearly see here that the pinning of grain boundaries in S1 provides this sample with a grain size that is a third, is like 3 times smaller than the reported grain size of S2. Moreover, S1 keeps a relatively constant grain size, and this is mainly because of L21 pinning the grain boundaries, refusing to dissolve even after 12 hours of aging. But for the case of S2, a constant increase in grain size is observed as aging time is prolonged. Now, in order to quantify the mechanical properties of both S1 and S2 at their multiple heat-treated conditions, we use Beaker hardness testing. We set the parameters to be 300 gram force with 10 seconds dwell time, and the data points that you see here in the figure correspond to an average of 10 indents. While the ASCAS and homogenized hardness of both samples is basically the same, the hardness of S1 is clearly outmatches S2. Peak aging hardness for both samples is reached at 4 hours, after 4 hours of aging, and S1 reaches a record high hardness of 717 HV, while S2 reaches a value of 581 HV. Moreover, you see, based on the sort of like plateau shape of the data points describe, that the peak aging remains relatively constant even after 12 hours of aging. Finally, here at the bottom of the figure, you can see that for the sake of comparison, the peak aging hardness of an HSLA 115 strengthening with copper and M2C carbide is plotted, such as to indicate as a reference how good our samples are doing when it comes to hardness, which testifies of the efficiency of L21 as a precipitate strengthening particle in the context of the HSLAs. In order to fully explain this hardness difference, we need to look deeper into the microstructure. This is allowed by the atom probe tomography. Here you can see 2 needle samples of S1 and S2 detailing the existence of both L21 and copper nano-sized precipitates. These images clearly show a distinct volume fraction and size between the precipitates in both samples. S1 has a much finer and dispersed population of both L21 and copper than S2. These then, by Orwan and Xiong hardness theory, can explain the difference in hardness in the age condition shown in the previous slide. Moreover, retrieving APT-element contours allow us to identify cluster of elements independently. With this, precipitates rich in copper and titanium and silicon are clearly identified, but also a finer solubility of aluminum and niobium is also confirmed. This reinforces the idea of niobium acting as a heterogeneous nucleation site in the grain boundaries, which then allows the formation of L21 as seen in the homogenized and age microstructure for S1. Clearly, because S2 has so much less niobium, this effect is not being, it doesn't happen in the S2. So evaluating the age microstructure evolution in time with APT, we can observe that the volume fraction and size of precipitates does not change much between the 4 and the 12-hour age samples, confirming then why the peak aging hardness remains constant even after long aging times. The volume fraction of copper in these samples is similar to the one reported on previous HSLA studies strengthening by copper and M2C carbides, between 1 and 3%. However, having a range between 5 to 8% volume fraction of L21 confirms the advantage of this intermetallic phase as a suitable strengthening precipitate phase. Finally, a detailed look of these APT images and the use of proximity diagrams allows to not only identify the composition of these precipitates, but also to confirm that co-precipitation interaction occurs between the copper and the L21 precipitates. Here we have, for the case of S1 age at 4 hours, we see on the figure to the left that the silicon and titanium content increases in the proximity of the interface between the ferrite and the copper precipitate. This same behavior is portrayed in the case of copper content increasing in the vicinity of the interface between the L21 and the ferrite phase. If we look at the 12 hours age sample S1, we see the same behavior. We see an increase of titanium and silicon in the vicinity of the interface between copper and ferrite, and then we see copper content increasing close to the interface between the ferrite and the L21 phase. Another important feature to highlight from this plot is that you can see that when looking into the interface between ferrite and L21, has that interface, which means at the nucleus or closer to the nucleus of the L21 precipitate, we see an increase in niobium, which then confirms the final solubility that L21 has of niobium in the case of S1. For completion, we also have the proximity diagrams of S2 age at 4 hours and 12 hours, and we see a very similar behavior. Even in this case, it's more clear precisely because of the bigger size of the precipitate. Finally, here's the 12 hours age S2, and again, we see how the copper content increases in the vicinity of the interface between the ferrite and the L21 phase. As for conclusions, in order to wrap up this presentation, we can say that we have effectively designed an HSLA steel strengthening by L21 as its major strengthening precipitate. We have seen that aging at 500 degrees C for 4 hours yields a record peak aging hardness in both samples. We see that the L21 phase can lead to grain refinement by grain boundary pinning associated with the final solubility of niobium that it might have. We also have shown the co-precipitation behavior between L21 and copper precipitates in the samples. We have also shown that peak aging hardness remain constant even after 12 hours of aging. This is explained because of the relatively constant precipitate fraction and size in the age samples. And finally, S1 shows a smaller and more abundant volume fraction of precipitate than S2, which then, combined with a more refined grain size, explain its reported 20% higher hardness. Lastly, we can quickly just point out a few comparisons between the simulation and the experiment results in order to assess the efficiency of CALPHAD at predicting these systems. We see that CALPHAD is not fully accurate at predicting the phase fraction in HSLAs. This is mainly related to the showing up of the L21 in the homogenized sample, the S1 homogenized sample. But this is tied up with the fact that the L21 is modeled as a line compound with no solubility, but results, the APT results and the EDS results have shown that there exists a final solubility of niobium and aluminum in the L12. So we propose an improvement on the CALPHAD database regarding the L21. But also, we should say that both CALPHAD and our aging model were accurate at predicting the volume fraction of L21 since the reported values of APT ranges between 5 and 8%. Thank you very much for listening to this presentation, and thank you very much for for the committee of MSNT to put together this virtual edition. We're very thankful for the opportunity to be able to participate. If you have any questions, feel free to just email me at rar126@peta.edu or just contact us through our lab website listed here. And yeah, thank you very much, and have a good rest of your day.